There's a signal reaching Earth right now that left its source 22.5 hours ago. It is coming from a machine 15 billion miles away, moving through a region of space where no human-made object has ever been. That machine is Voyager 1, and for the past 18 months, it has been sending back measurements that have quietly overturned nearly everything scientists thought they understood about the space between stars. This is not about a malfunction. This is not about corrupted data. This is about direct observations from inside interstellar space, revealing that the models built to describe that environment were based on assumptions that turned out to be fundamentally wrong. The researchers analyzing this data are not using careful academic language anymore. They are using words like shocking and completely unexpected, and we need to rethink this from the beginning. What Voyager 1 found is not dangerous. It is not heading toward Earth. But it is forcing physicists to reconsider basic assumptions about the structure of the galaxy, the behavior of plasma in deep space, and the nature of the boundary that separates our solar system from everything beyond it. If you want space content that does not treat you like a child, subscribe to Space Horizon, because we are about to go deep into data that most channels will not touch. Let us begin. To understand what Voyager 1 just sent back, you need to understand where it is and what it is actually measuring. Voyager 1 launched in September 1977. It flew past Jupiter in 1979 and Saturn in 1980, then continued outward, using the gravity of those planets to accelerate into deep space. By August 2012, it had traveled so far that it crossed the Heliopause, the boundary where the solar wind from our sun stops pushing outward and the pressure of interstellar space pushing inward takes over. That crossing made Voyager 1 the first human-made object to leave the solar system and enter interstellar space. Not metaphorically. Physically. Everything inside the Heliopause is part of our solar system. Everything outside is the space between stars. As of early 2026, Voyager 1 is roughly 15.3 billion miles from Earth and still moving outward at about 38,000 miles per hour. The radio signal it transmits takes 22.5 hours to reach us, traveling at the speed of light. The spacecraft carries several scientific instruments, but the one producing the data that has scientists rethinking interstellar space is called the Plasma Wave Subsystem. This instrument does not take pictures. It does not measure temperature or chemical composition. What it does is detect oscillations in the density of charged particles in the surrounding plasma. Think of it as listening to vibrations in the fabric of space itself. Before Voyager 1 crossed into interstellar space, every scientific model describing that region predicted it would be relatively quiet. A thin, cold, sparse plasma with very little structure. Occasional bursts of activity when shock waves from the sun traveled outward and disturbed the interstellar medium. But between those events, mostly calm, mostly uniform. The models were built using observations from Earth combined with theoretical physics, and they had been peer-reviewed, tested, and accepted for decades. Voyager 1 walked into interstellar space and immediately started detecting something no model predicted. A persistent, continuous emission in the plasma. Not a burst, not a temporary disturbance. A steady, low-frequency hum that has been present in every measurement since 2017, stretching across more than 900 million miles of interstellar space. The first scientific paper describing this emission was published in Nature Astronomy in November 2021 by a team led by Dr. Stella Ocker at Cornell University. The researchers were cautious in their language, but the implication was clear. Interstellar space has structure. It has density variations. It has turbulence at scales ranging from meters to millions of miles. The quiet uniform void the models described does not exist. That discovery alone was significant, but what came next is what has the field in genuine turmoil. In March 2024, Voyager 1 experienced a serious malfunction. A memory chip in its flight data system failed after 47 years of operation, and the spacecraft began transmitting corrupted, unreadable data. Engineers at NASA Jet Propulsion Laboratory spent 5 months diagnosing the problem remotely across a 45-hour round-trip communication delay. They eventually found a way to relocate the corrupted software, and in July 2024, Voyager 1 came back online. When it resumed transmitting clean data, the plasma wave instrument showed something new. The persistent emission Voyager had been detecting since 2017 had changed. Not disappeared, changed. The frequency had shifted, the amplitude had increased, and the pattern of oscillation was showing variations that suggested the spacecraft was moving through regions of interstellar space with dramatically different plasma densities. Dr. Ocker and her team published a follow-up analysis in September 2025, and this is where things get uncomfortable for existing theory. Using data collected between July 2024 and June 2025, They calculated the electron density in the interstellar medium along Voyager 1's trajectory. What they found was that plasma density was not uniform. It varied by factors of 2 to 3 over distances of just a few 100 million miles. To put that in perspective, imagine you are measuring the density of air in a room, and you find that one corner has twice as much air as another corner just a few feet away with no barrier separating them. That does not happen in a stable, uniform environment. That happens when something is actively structuring the medium, when there are forces or processes at work that the models did not account for. The question researchers are now asking is what is creating that structure? There are a few possibilities. The first is that interstellar space is filled with turbulence left over from ancient supernova explosions. When massive stars explode, they blast enormous amounts of gas and energy into space. That material expands outward, forming bubbles and shock fronts that can persist for millions of years. Voyager 1 might be flying through the remnants of supernovae that exploded long before our solar system even formed. The second possibility is that the structure Voyager is detecting is caused by interactions between different streams of interstellar gas moving at different velocities. The galaxy rotates, but not as a solid object. Different regions move at different speeds. Where those regions collide or shear past each other, they create boundaries and density gradients. Voyager might be crossing through one of those shear zones right now. The third possibility is the one that has implications reaching all the way back to Earth. The Heliopause. The boundary of our solar system is not a static fixed shell. It moves, it breathes, it responds to changes in the solar wind and to pressure variations in the interstellar medium outside. If the interstellar medium is more turbulent and more structured than models predicted, then the heliopause itself is probably more dynamic and less stable than we thought. That matters because the heliopause is not just a boundary line on a map. It is a shield. It deflects a significant fraction of the high-energy cosmic rays streaming through the galaxy, preventing them from reaching the inner solar system at full intensity. Life on Earth exists in part because the heliopause reduces the radiation environment in our neighborhood. If that shield is less stable than models suggest, if it fluctuates more dramatically in response to interstellar conditions, we do not fully understand, then our assumptions about long-term radiation exposure for life on Earth and for future deep space missions need to be revisited. Now let me show you exactly how significant the density variations Voyager detected actually are. Between 2017 and 2020, the plasma density Voyager measured averaged around 0.055 electrons per cubic centimeter. For context, the best laboratory vacuum chambers on Earth contain about 100 million particles per cubic centimeter. Interstellar space is empty in a way we cannot replicate. But even in that emptiness, the density Voyager measured was relatively stable. Then, in mid-2020, the density began to climb. By late 2020, it had reached 0.13 electrons per cubic centimeter, more than double the earlier value. It stayed elevated through 2021 and into 2022. Then after the 2024 malfunction and recovery, when Voyager resumed science operations, the density measurements showed the spacecraft had entered a region where plasma density was fluctuating between 0.08 and 0.14 electrons per cubic centimeter over timescales of just weeks to months. That kind of variation over those distances does not fit any pre-Voyager model of the interstellar medium. The models predicted slow, gradual changes over thousands of astronomical units. What Voyager is seeing is rapid variations over hundreds of astronomical units. Something is structuring the plasma at scales far smaller than theory suggested. Dr. Ocker told reporters in November 2025 that Voyager 1 is giving us our first real look inside interstellar space, and it is not what we expected. The medium is not smooth. It is not uniform. It has weather. It has texture. And we had no way of knowing that until we put an instrument out there. But there is more. In January 2026, a separate team led by Dr. Jamie Rankin at Princeton University published an analysis of Voyager 1's magnetic field data. The spacecraft carries a magnetometer that has been continuously measuring the strength and direction of magnetic fields since it crossed the Heliopause in 2012. What Rankin's team found is that the magnetic field in interstellar space is not behaving the way galactic magnetic field models predict. The galactic magnetic field is generated by the movement of charged particles on enormous scales, spanning thousands of light years. Models predict it should be relatively smooth and organized with field lines running roughly parallel to the plane of the Milky Way. What Voyager is measuring shows something different. The field direction is changing on much shorter timescales and much smaller spatial scales than a large-scale galactic field should. One possible explanation is that Voyager is detecting localized magnetic structures. Magnetic flux ropes, or magnetic bubbles, created by turbulence in the interstellar plasma. These structures can be generated when plasma flows with embedded magnetic fields collide and reconnect, releasing energy and creating tangled, twisted field configurations. If that is what Voyager is seeing, it means the interstellar medium is magnetically active in ways current models do not capture. The alternative explanation is more radical. It is possible that our models of the galactic magnetic field are incomplete, that the field has structure at scales smaller than we can observe from Earth, that what looks smooth and uniform when viewed from inside the solar system is actually complex and textured when you're sitting inside it 15 billion miles away. Testing that idea will require data from a second interstellar probe, which currently does not exist. Voyager 2 crossed the Heliopause in November 2018, 6 years after Voyager 1. It is now also in interstellar space, but traveling in a slightly different direction. Comparing measurements from both spacecraft gives researchers 2 data points instead of 1. Early comparisons published in mid-2025 show that the plasma density and magnetic field variations Voyager 1 is detecting are not identical to what Voyager 2 is seeing. That confirms the variations are real and local, not instrumental errors. But 2 data points are not enough to build a complete picture. Interstellar space is vast. The region between stars and our local neighborhood alone spans trillions of miles. Voyager 1 and Voyager 2 are sampling 2 infinitesimally small threads through that volume. Drawing broad conclusions from that is like trying to understand Earth's weather by placing 2 thermometers in different cities and nothing else. What researchers need is more probes, more measurements, more data points. But here's the problem. Voyager 1 and Voyager 2 were launched in 1977 using technology from that era, and they have been operating for nearly 50 years. No mission currently planned or funded will reach interstellar space in the next 25 years, when Voyager 1 and Voyager 2 finally go silent. Sometime in the early 2030s, the only real-time observational window humanity has ever opened into interstellar space will close, and it will stay closed for decades. That makes the data Voyager 1 is sending back right now irreplaceable. Every measurement it takes, every oscillation it detects, every magnetic field reading it transmits is information we will not have another opportunity to gather for a generation or more. The scientists working on Voyager data are acutely aware of this. They are not just analyzing observations, they are racing against a clock that cannot be stopped. As of February 2026, Voyager 1 is running on approximately 240 watts of power, down from 470 watts at launch. It loses about 4 watts every year as the plutonium in its radioisotope generators decays. NASA has already shut down 7 of the 10 scientific instruments the spacecraft launched with. The Plasma Wave instrument is still running, but every year the mission team has to make harder decisions about what to keep operational and what to turn off to conserve power. There is an effort underway to extend the mission as long as possible. Engineers tested a procedure in mid-2025 to redistribute power more efficiently across Voyager 1's remaining systems. If successful, it might buy another year or 2 of operations. But the end is inevitable. Sometime between 2028 and 2032, the power level will drop below the minimum needed to run any instrument, and Voyager 1 will go silent. When that happens, it will not stop moving. There's nothing in interstellar space to slow it down. It will continue traveling at 38,000 miles per hour in a straight line away from the solar system for thousands of years. In about 4,000 years, it will pass within 1.6 light years of a star called Gliese 445, but it will pass in silence. No data, no signal. Just a machine carrying a gold-plated record with sounds and images from a planet it left behind. For now, the signal is still coming. 22.5 hours of travel time across 15 billion miles of empty space. And every transmission carries information about an environment we thought we understood, but clearly did not. The interstellar medium is not a void. It is not quiet. It is structured, turbulent, and dynamic. It has density variations that models never predicted. It has magnetic complexity that theory did not anticipate. And the only reason we know any of this is because one small machine built with 1970s technology kept going long enough to get there and tell us what it found. If this is the kind of space science you come here for, subscribe to Space Horizon right now. We cover the discoveries that matter explained with the depth they deserve. Turn on notifications so you do not miss the next one. Leave a comment and tell me what you think is causing the density variations Voyager is detecting. Is it turbulence from ancient supernovae? Is it shear zones between different streams of interstellar gas? Or is there something else happening out there that we have not thought of yet? The scientists studying this data do not have a final answer, and I want to know what you think. Share this video with someone who thinks space is empty, because it turns out the space between stars is anything but. Voyager 1 is showing us a universe more complex, more active, and more mysterious than the models ever suggested, and the data is still coming. Thanks for watching Space Horizon. We will see you in the next one.